Welcome everyone. So this is design of steel structures and I'm Engineer Ronjan R. Garmi. So today we are going to discuss the design of tension members. So tension members design. Previously we have computed about the concept of LRFD and ASD. On the load resistance factor design, we are considering the sum of all the loads. And these loads are being factored, or meaning the sum of the factored loads. So in that case, we can now determine the load capacity or the strength derived from the known members. So remember, last time, the members are known. Likewise, for allowable strength design or ASD method, we sum all of the allowable loads, wherein these allowable loads should not exceed the capacity of the known members. Again, the known members are actually our basis. So another thing that we have discussed last time is the calculation of the net area, the effective net area, the gross area. So those principles will be applied here, in which vice versa, instead of calculating for the capacity of the known members, this time the members will be predetermined. Hence, our basis in determining the appropriate section is the loading. Therefore, in the design procedure, we should satisfy the following. First, for the load resistance factor design, wherein the design strength is PU, where PU is also known as the factored loads. So the concept here is that the factored loads should always be less than the capacity of our member, and that is given by phi times Fy times Ag, or the gross area. So we have emphasized that the pair of Fy is Ag because this is the yielding zone or the yielding condition of our design. So we use phi is equal to 0.9 with respect to yielding. So by that, we can determine the required gross area through the formula Pu all over 0.9 of Fy. So when we talk of yielding, this is actually the upper limit of the required area. So for the lower limit, actually, we are referring to the fracture condition of the member. Hence, LRFD still expresses the loading into factored loads, wherein these factored loads should be always less than or equal to phi times Fu times Ae. So again, it was emphasized previously that the pair of Fu is the effective area. So for phi for fracture, we normally use 0.75 for LRFD. So therefore, the required area, effective area, should be greater than or equal to Pu all over 0.75 of Fu. So this is for fracture, which will be considered as the lower limit. For ASD, the allowable strength is given by P sub A, or this is the allowable load. The concept is that the allowable load should always be less than or equal to the allowable capacity of the tensile member. So likewise, on that LRFD, we also have upper limit, the yielding, wherein Fy is always paired to Ag. This time the factor will be 0.6, given that it was derived from the reciprocal of the omega, which is equal to 1.667. So Ag required will always be greater than or equal to the allowable load PA all over 0.6y of Fy. For yielding, this is the upper limit, that equation. So for fracture, of course, we pair Fu to Ae with the factor of 0.5. 0.5 is derived from the reciprocal of the omega, which is equal to 2 for fracture. Hence, we can conclude that the effective area should always be greater than or equal to PA all over 0.5 of Fu. So this is the lower limit, similar to that of the LRFD. So aside from those concepts that we need to satisfy, we should also adhere to the minimum slenderness ratio, L over R. L is the length and R here is the radius of gyration of our member. So in our strength of materials, we have known this equation. The square of the radius of gyration is equal to the quotient of the moment of inertia all over the area of the cross section. Solving for R, we can have the right hand side of the equation to be equal to square root of I all over A. So this is the radius of gyration. The moment of inertia is I, and A is the cross-sectional area. Now going back to the slenderness ratio L over R, L over R should not exceed 300. L is the member length, R is the radius of gyration. By the way, this minimum slenderness ratio, according to AISC, is also applicable to the SI units. So this provision is applicable to SI and English units. So let us apply those to a certain problem. Here, the tension member with a length of 5 feet 9 inches must resist a service load, the dead load, of 18 kips and a service live load of 52 kips. So our task is to select a member with a rectangular cross-section. In here, we use 836 steel and assume a connection with one line of 7/8 inches diameter bolts. So we recall the combinations for LRFD, since LRFD deals with the factored load. And the significant combination here is the combination 2, considering only the dead load and the live load. That is 1.2 dead load plus 1.6 live load. So going back to the problem, by LRFD we can now get the factored load by that combination. So we simply substitute the dead load and then multiply it by 1.2 as well as the live load 52. So by that combination, we can arrive to 104.8 kips. And then if we know PU, of course, we can now compute for the required AG. So the required AG is given by equation PU all over 0.9 of Fy. So we remember that Fy is 36 for yielding, Fu is 58 KSI for fracture. Therefore, the required AG, we'll just have to substitute 104.8 or the factored load and the Fy 36. By that, we can now arrive at the required gross area, that is 2.32235 square inches. Now this is the upper limit of our area. So therefore, when we say upper limit, we should exceed this upper limit. So meaning the section should not have a value that is lesser to this gross area. So computing now for the effective area, we have this expression PU all over 0.75 of Fu. Therefore, the required effective area, we'll just have to substitute again 104.8 as our factored load and Fu 58. Hence, we can arrive with an effective area of 2.409. So when we select a certain member, we should have an area, gross area, greater than 3.235 and an effective area greater than 2.409 square inches. That is the concept here. So in this case, we have a trial thickness of 1 inch. Why do we have to assume a 1 inch thickness? Because as an initial trial, we peg the area equal to AG, because the gross area is just simply the width times the thickness. So doing that, of course, the net or the gross width will be just equal to your gross area, 3.235 inches, having a 1 inch thickness. So this gross width is still acceptable to the fact that it is equal to 3.235, which is the limit. So still, it is equal to 3.235. It is not less than 3.235. So therefore, we can round our width to 3.5 because the section do not have an exact width of 3.235. So the nearest available section to that width is 3.5 inches. So therefore, the trial section would be equal to 1 by 3.5. So in this case, we recall our knowledge on the reduction factor U, because in this calculation we are actually concerned with the net area, and the net area will just have to be multiplied to the reduction factor U to make it an effective area. So therefore, the effective area here, considering the net area, we just have to multiply it by the reduction factor U. So in this case, we are dealing with plates. So therefore, generally, U will just be equal to 1 since it has only one element. So the effective area therefore is equal to AN in this case because we are dealing with plate. So knowing that A is equal to AN, we just compute the AN to be equal to the gross area. Of course, we deduct the effective area of the holes. Hence, the effective area will be given by the AG, which is 1 by 3.5. We deduct the area of holes. Of course, the diameter is 7 over 8. As usual, we are going to add 1/8 to get the nominal area occupied by the bolt. So in here, according to the problem, we have one line of diameter bolts, so we just have to multiply it by 1. So consequently, we can now have our effective area 2.5 square inches. Now, this effective area should be compared to that of the required effective area. And that required effective area is actually 2.409. We can see here that 2.5 square inches is greater than the effective area. Therefore, the effective area is sufficient enough to resist the loading. Now, moving to the allowable strength design. Just the same, in here, we should have an allowable load. It should be PA. So, PA is barely the sum of the dead load and the live load because ASD do not have a factored loading. So, we directly add 18 to that of 52 live load. So therefore, we can arrive at 70 kips. So 70 kips will be our basis for the required gross area. We divide that by 0.6 of Fy. Okay. So the required gross area now will be equal to 70 all over 0.6 all over 36. So therefore, the required gross area will be equal to 3.24 square inches. Likewise, for the required effective area, we have PA all over 0.5 of FU. So the required effective area is 70 all over 0.5. Substitute 58 FU for fracture. So it will yield to 2.414 square inches. So given this required gross area and the required effective area, we will again have a trial thickness. So from the trial thickness, automatically WG will be also equal to the gross area of the section. So again, 3.24 inches is the net width, and the nearest section with the width of 3.24 is 3.5 inches. So therefore, similar to that to the LRFD, the trial section is 1 by 3.5 inches. So we calculate our effective area using the trial section. So the trial section has a gross area of 1 by 3.5. We deduct the holes Okay. Thickness here is 1. By the way, 1 should be outside that expression. Okay. So the effective area will be equal to 2.5 square inches. So comparing that to the required effective area, still it exceeds the requirement. We remark it as okay. So we have satisfied the first condition with regards to the required gross area and the effective area. Now we check the slenderness ratio L over R. So the provision is that the slenderness ratio should not be greater than 300. So first, we calculate the radius of gyration of our section. So the radius of gyration is given by the square root of I over A, wherein I, for a rectangular section, since we have a plate here, I is just equal to BH cubed all over 12. Now, before we are going to substitute the base and the height, of course, we should determine what is the base and the height. So, given that our loading is parallel to this plate, the perpendicular line to that loading will be our base, and the other dimension should be our height. So, going back to the formula, of course, we just substitute the base of 3.5 and the height of 1. 1 here is the thickness. So, substituting that, we will yield to an I of 0.2917 inches to the fourth. Knowing I, of course, we go back the calculation of the radius of gyration, wherein we just substitute 0.2917. Our area is 3.5 because the section derived was 1 by 3.5 inches. So therefore, the radius of gyration is 0.2887. So we now proceed to the mother equation, L over R. Of course, the length given is 5 feet and 9 inches. 5 feet and 9 inches should be converted to a total of inches. So 5 feet will be converted to inches. So therefore, we should multiply 5 by 12 and then add the 9 inches. So that would lead to 69 inches. So we now substitute those values to the slenderness ratio L over R. So this will be equal to 239, which is less than 300. So again, this provision was satisfied. So therefore, PL 1 by 3.5 is adequate to use. So that is all about the design of tension members. So let us take another example. So this time we have an angle with an equal leg. So L here, or the tension member length, is 15 feet. This is to resist a service load of 35 kips and a service live load of 70 kips. We use A36 steel. Okay, we take note of the strength here in kips. So this is the configuration of the connection. So that is an angle of an equal leg. So the service loads are given. Of course, LRFD first. We get the factored load, PU, by the combination. Okay, substitute the values. 35 for dead load and 70 for live load. That will be equal to 154 kips. So from here, you can now compute for the required gross area. The required gross area is equal to PU all over 0.9 of Fy. So all we need is to substitute those values and come up with the required gross area equal to 4.75 square inches. For fracture, we can consider the required effective area. So now we will be dealing with Fu. So we just have to substitute the values, 154 for the factored load and 58 for our Fu. So therefore, the required effective area will be equal to 3.54 square inches. So we would want to determine this provision. Of course, L over R should less than 300. So on the previous example a while ago, we are just dealing with the plate. So therefore, the calculation is straightforward. Unlike here on the angle, we need to determine first the minimum radius of gyration. When we say minimum, your radius of gyration of the selected member should be greater than the derived radius of gyration. Because of this provision, we set our limit to 300, but substituting and interchanging your R and 300 by cross multiplication, R can be solved. The length here is equal to 15. We have to multiply by 12 to make it in inches. So therefore, the radius of gyration minimum should be equal to 0.6 inches. So we summarize all the requirements here. The required gross area is 4.75 inches squared. The required effective area is 3.54 square inches. And then the minimum radius of gyration is 0.6 inches. So what we do is to look into the table of the angle of an equal leg with these requirements. Okay. So this is the requirement actually. And then from the table, we can now see various area. Of course, on the fourth column of our table, we should seek for an area that is nearest to 4.75 square inches. As much as possible, it should be greater. Okay? But in here, it is glaring that we can select the member L6 by 4 by 1/2. Why? Because it is the member with an area nearest to the required AG of 4.75 square inches. So with that, we will take this value 4.72 and check the radius of gyration, the largest one, 0.865, actually satisfies on the provision of the minimum radius of gyration of 0.6. So we have no problem on that. So therefore, can now compute for the net area using this trial section. The net area is equal to 4.72. So let me give it. Of course, we are going to deduct those holes, 3/4 plus 1/8. Again, this 1/8 is always be added to our diameter. And the thickness is 1/2. Okay. By the way, what we have selected here is the section L6 by 4 by 1/2. So therefore, the thickness is 1/2. And there are two connections or two rows of connections on the configuration of our plate or angle bar. So the net area therefore will be equal to 3.845 square inches. So 3.845 square inches will be translated to the effective area by multiplying a reduction factor U. Okay? So a while ago, we are just dealing with plate. That is why U is equal to 1. Consequently, that the net area happened to be equal to the effective area. But this time, we have an angle, so that we are going to refer to the alternative method in order to derive, okay, or we get the derived U from the alternative method. So here, recall that for 4 or more fasteners in the directions of loading, we have U is equal to 0.8. So this shall be adapted into the problem. So therefore, the effective area is 0.8 times the net area, 3.845. Hence, the effective area will be equal to 3.08 square inches. Now, comparing this 3.08 to our required AE, it is actually less than that required AE. So, the indication of that is the cross-section chosen would not be sufficient enough to resist the loading. Hence, we tag that as NG or no good. So, let us try another section. Okay. So, this time, we wanted to increase our trial section or trial area among the sections. Why? Because as calculated, your gross area was sufficiently reduced because of the reduction factor. Hence, the section next to 4.75, okay, is L5 by 3.5 by 5/8. So this has an area of 4.93. So it has a greater values, slightly greater than 4.75 square inches. So the radius of gyration is checked here, so that must be compared to the radius of gyration minimum of 0.6. So again, we have no problem on that because 0.746 is much greater than 0.6. So calculating for the net area, we have the gross area 4.93. We deduct again the area occupied by the holes. We have 3/4 plus 1/8. Of course, this time the thickness is 5/8. Okay? And there are 2 rows of connection. Therefore, the net area would yield to 3.836 square inches. Now, comparing that, okay, before we compare, of course, net area shall be converted or translated to the effective area by multiplying the net area to the reduction factor U. So again, we adopt 0.8 in here, okay, times 3.836. The net area is 3.07 square inches. So we compare that to the required. Again, it is lesser than that of the required. So therefore, it's no good. Okay. So I would like to reiterate here to avoid several trials as presented. What we do from these requirements, we know that the reduction factor that must be considered here is U is equal to 0.8. Having that, when our trial area eventually reduced by 20%, therefore, we anticipate to increase the trial area by 20%. So we'll be having a trial area net, that will be equal to, okay, the requirement, the gross area requirement is 4.75. Now, because of 0.8 reduction, therefore, we tend to increase it by 20% or 1.2. Okay? So, U 0.8 is actually reducing your area by 20%. So, therefore, in anticipation, we increase the trial area by 20% also. Okay, so by that calculation, we can arrive at 5.7 square inches. Of course, the nearest to 5.7 inches will be the section L8 by 4 by 1/2. So this has cross-sectional area 5.8. And again, the radius of gyration is greater than the minimum required radius of gyration of 0.6 inches. So by that, you just have to compute the net area as usual. We have 5.8 less the holes 3/4. We always add 1/8 here. Then multiply it by the thickness 1/2. And there are 2 rows of bolts connection. So therefore, the net area will be equal to 4.925. And then from that, we get the effective area by multiplying 0.8 to that net area. The effective area now is 0.8 times 4.925. Hence, we will have a value of 3.94 square inches for the effective area. So this time, it's really greater than your required effective area. Hence, we tag that as adequate or okay. Now, for ASD method, the only difference is on the derivation of the loads. This time, we are dealing with the allowable loads. We have barely adding the dead load and the live load. Again, ASD does not require factored loads. So, PA is 35 plus 70. That is equal to 105 kips And that from 105, we can now derive the required gross area. And also, substituting the value of Fy, 36, we will have a gross area 4.86 square inches. For the required effective area here, we perform the equation PA all over 0.5 FU and then arrive at 3.62 square inches. Again, we will derive our required radius of gyration. We'll have 0.6 inches. So to summarize, we have these values. The required AG, 4.86. The required effective area, 3.62. And the minimum radius of gyration of 0.6 inches. Now we refer to table. So of course, we wanted to have a trial net area 4.86 by 1.2, expecting that we have a 0.8 reduction factor in a while. Of course, 0.8 is reduced by 0.2, so therefore we increase the trial area by 20% also. And that will be equal to 5.832 square inches. So the nearest to 5.832 is also L8 by 4 by 1/2, having an area of 5.8 square inches and a radius of gyration far greater than 0.6 minimum. So just the same, we compute for the net area, 5.8 less the holes. Of course, 1/8 is always added here. The thickness here is 1/2 and there are 2 rows of connection. So we'll arrive the net area 4.925 square inches. So from here, we can compute for the effective area by multiplying again the reduction factor to that net area, and the reduction factor is 0.8. Okay, so we multiply that one and then we can arrive with a value of 3.94 square inches. So we compare this to the required effective area. So it is now greater than the effective area, 3.62 square inches. Hence, we tag this as OK. So therefore, the shape satisfies all requirements, whether it is LRFD or ASD. Hence, therefore, we can use the section L8 by 4 by 1/2. So this is the answer, or the adequate section for that service loads. So this ends our lecture for today. Thank you, class, and have a good day.